Hi everyone, welcome to Chapter 2, which is all about the chemical foundations of life. Before we get into any content of Chapter 2, we are going to start off with a checkpoint that requires a little bit of review from the first chapter. And in this checkpoint, what I want you to do is name 3 of the 8 characteristics that are shared by all living organisms that we learned about in Chapter 1. Name 3 of the 8 characteristics. Hopefully this checkpoint jogs your memory about some of the things that we learned in Chapter 1 about what unifies living organisms, and we're going to use it as a way to transition into Chapter 2, the chemical foundations of life, by reminding you that one of the characteristics that is shared by all living organisms is that of order. In Chapter 1, we discussed how all living things have an organized composition and that organization is similar from living organism to living organism. In particular, on the very most basic level, living things are constructed of molecules, which are organized into structures called organelles, which are organized into cells, tissues, organs, organ systems, and organisms. And I also mentioned that in our very first unit, we are going to be moving through macromolecules, organelles, and cells. And we're going to start at the most basic level, the molecules. So in order to do that, we need to understand some things about chemistry, because we can't talk about molecules and the composition of living organisms on a molecular level unless we understand some of the chemical principles that underlie these concepts. So that's what this chapter is dedicated to doing. We're going to start off very basic. So at the most basic level, chemistry is concerned with things that are made of matter, which is the substance of which every object in the universe is made, technically defined as anything that occupies space and has mass. Matter itself is composed of smaller particles, which are called atoms, or associations or groupings of those particles, which are called molecules. One thing that I like about this picture that you see on the slide is that it shows living organisms depicted as a collection of tiny atoms put together, which is what we really are. It is estimated that the average human body contains somewhere around 7 to the 27th power atoms, which is the number 7 with 27 zeros after it. That's how many atoms are in the human body. So atoms are considered the basic unit that comprises matter. But for how small they are, there are still particles that are smaller than atoms and that make up the structure of an atom. So within the structure of an atom, there is a consistent arrangement where there is a central cluster of particles that is called the nucleus. And then around the outside of that nucleus, there are at least one ring called an orbital. And in this atom that you see on the screen here, there are 2 rings, 2 orbitals. It was hypothesized for many years that this is what the structure of an atom looks like. However, that was not confirmed until 2013 when the first microscopy image of an atom was published by the American Physical Society. Before this point, microscopes had not been powerful enough to actually capture an image of an atom because they are so small. But in this image, the first ever image, you can see that there is indeed a central cluster of particles that is surrounded by rings called orbitals. So yes, the structure of an atom that was hypothesized for many years is in fact true. So here's a little bit more about that structure. Within the nucleus and the orbitals, there are 3 different what are called subatomic particles. They're called subatomic because they are within the structure of an atom. Protons are one of those 3 particles, and they are positively charged and located within that central cluster called the nucleus. So in this image right here, we can see that the protons are indicated as the purple circles. Neutrons have no electrical charge, and they are also located in the nucleus alongside the protons. In this image, the neutrons are indicated in the light blue circles. And then finally, electrons have a negative electrical charge, and they are found in the orbitals that are orbiting the nucleus in the center of the atom. And these are indicated in the little orange circles that you see. Now, protons and neutrons both weigh the same amount. They both weigh 1 Dalton, which is a tiny unit of measurement of mass. much, much smaller than a pound or even a gram. The mass of an electron is so small compared to the mass of a proton or a neutron that it doesn't even matter. It is not considered for our purposes when we're talking about the mass of an atom. So that means that the mass of one atom, any given atom, is going to be in Daltons the equivalent of the number of protons plus the number of neutrons, because each of those weighs 1 Dalton, and the electrons are so tiny compared to protons and neutrons that we don't even consider them. So this brings us to our next checkpoint of the lecture. Here we have a carbon atom represented. In this case, we have the electrons in blue, we have the protons in red, and the neutrons in green. What I want you to do is tell me in Daltons what is the mass of this atom right here. So this chart right here summarizes things nicely. 3 different subatomic particles, protons, neutrons, and electrons. Protons have a mass of 1 and an electrical charge of +1. Neutrons have a mass of 1 but no electrical charge. And electrons have no mass but an electrical charge of -1. Now that we have an understanding of what an atom is, we can talk about another related concept, which is that of an element. So all the atoms in the universe are categorized into different groups that are called elements based upon the number of protons that are found in the nucleus. Atoms that have the same number of protons in their nucleus are said to belong to the same category, and that category is considered one particular type of chemical element. Now, if you've seen the periodic table before, which is what's displayed on the right-hand side of this slide, then you have seen a picture of what are all of the known elements in the universe. If we zoom in on one of these squares on the periodic table, then we can see that there are a few different features presented on this square. So at the very top, we have something called the atomic number. And the atomic number is the number of protons that are found in that particular element. In other words, it is the number that defines what that category is. How many protons are in that element is what defines the element. Underneath it, we have the elemental symbol, which in this case is C, representing carbon. Sometimes the element name is not present depending upon the periodic table, but in this case it is, and we can see that this is carbon. And then at the very bottom, we can see another number, and that is the atomic weight. So to recap, up at the top, the atomic number is the number of just protons. And at the bottom, the atomic weight, because remember, the weight of an atom considers both protons and neutrons. The atomic weight is the average number of protons and neutrons together. Now you may think that there's something fishy about the number at the bottom, the atomic weight, because it's 12.01. And we can't have fractions of protons or fractions of neutrons. We said that a proton weighs 1 Dalton and the neutron weighs 1 Dalton. So how can we have 12.01 as the average atomic weight? Where does that 0.01 come from? We're going to talk about that in just a second, but before we do, let's move back to the periodic table and take a look at the elements that compose living organisms. So there are 92 what are called natural elements found in the world, which means that they are found in nature. You don't have to tinker with them in order to get them to exist. There are many more elements that can be artificially synthesized in a laboratory environment, but there are 92 that occur naturally. Out of those 92, only 25 elements comprise living organisms. And those are the 25 that you see highlighted in some sort of color on this periodic table. 4 elements out of those 25 compose 96.3% of the mass of living cells. And those 4 are the ones that you see highlighted in orange here. That is the hydrogen, carbon, nitrogen, and oxygen. So overwhelmingly, living things are mostly composed of hydrogen, carbon, nitrogen, and oxygen, and the remaining elements, the other 21, come from the other ones that you see highlighted here. But we are mostly only 4 different things, which is interesting. Now let's get back to that average atomic weight that was a little bit troublesome because it was 12.01. So The question that we have in our minds here is, why is this number not a whole number? Well, it's because this is the average number of protons and neutrons in atoms of carbon. Atoms of the element carbon have an average atomic weight of 12.01. And to give you some perspective on this, let's think about averages in a way that applies more to our everyday lives. Let's say on the first exam in this class, everyone in the class gets 100%, which would be wonderful, except for one person who gets a 90%. What is going to be the average for that exam score for the class? It's going to be very, very close to 100%, but it's not quite going to be 100% because one person got under 100%. It's going to be 99 point something, right? For that same reason, the average weight of an element is not going to be spot on a whole number because there are actually different variants of elements that weigh different things. These are called isotopes. Atoms of the same element that have different masses due to different numbers of neutrons are called isotopes. Now, we already talked about how the protons are what define an element. The periodic table is based around different numbers of protons, so that can never change. Carbon will always have 6 protons, no matter what, because that's what makes it carbon. However, it can have more or less than 6 neutrons. Neutrons are the other component of the element that makes up its mass. So in carbon in particular, there are 3 different isotopes that are known in existence. One of them is called carbon-12. Carbon-12 is called carbon-12 because it has a mass of 12, and that mass is given by the fact that it has 6 protons accompanied by 6 neutrons in its nucleus for a total mass of 12. Carbon-13 is another isotope which has, again, 6 protons because it has to. That's what makes it carbon. But instead of having 6 neutrons, it has 7 neutrons, giving it a total mass of 13, which is why it's called carbon-13. And then finally, carbon-14 has 6 protons once again, but this version has 8 neutrons, giving it a total mass of 14. So 3 known isotopes. We saw on the periodic table that the average atomic mass of carbon was 12.01. And so it makes sense that when we look at the carbon in the universe, 98.93% of it is carbon-12. Almost all of it is carbon with a mass of 12. A little over 1% is carbon with a mass of 13, and almost none, a negligible amount, is carbon-14. This means when you average out the mass of all carbon that we are aware of on Earth, the mass comes out to just a little bit above 12. This is the case for all elements on the periodic table. If we take a look at nitrogen, for example, we can see that the average atomic mass of nitrogen is 14.007, so just a hair over 14. The percent abundance of the different known isotopes of nitrogen is that 99.6% of known nitrogen has a mass of 14, almost none has a mass of 13, and 0.4% has a mass of 15, which pushes the average just a little bit above 14, and that's what you see on the periodic table. So, next checkpoint here. Tell me, based upon this square, which you would see on the periodic table, how many protons are found in the nucleus of a magnesium atom. And after you've done that, keep that number in mind because you're going to need it to answer this next checkpoint. This table here shows the 3 stable isotopes of magnesium in the world: magnesium-24, magnesium-25, and magnesium-26. How many neutrons does each isotope of magnesium contain in its nucleus? Not protons, but how many neutrons? So at this point, we have talked about how protons are the subatomic particle that defines the category of an element. So they never change. We've also talked about how neutrons can change. And when they change, they represent different isotopes of a particular element, different atoms that have varying masses because they have different numbers of neutrons. The third subatomic particle is the electron. Those are the negatively charged particles that have no mass and are located in the orbitals of the atom. And it turns out that, like the neutrons, electrons can also change. And when electrons change, the atom becomes an ion. An ion is defined as a particle with an electrical charge due to having a different number of protons compared to electrons. Atoms are defined as being electrically neutral, meaning that they should have the same number of protons in their nucleus as they have electrons in their orbitals. And this causes their overall charge to be zero, because the 9 positive charges that you see in the nucleus cancel out the 9 negative charges that you see in the orbitals in this atom of fluorine, for example. -9 plus 9 together equals 0, electrically neutral. However, if the number of electrons changes, let's say it increases, for example, by going up by 1 electron, now, instead of having a neutral atom, you have what's called an ion. You still have 9 protons in the nucleus of this fluorine ion, because remember, 9 protons is what makes it fluorine. But now you have 10 electrons in the orbitals. And that means that there are 9 positive charges in the nucleus, but there are 10 negative charges in the orbitals. 9 minus 10 is an overall charge of -1. So this fluorine ion now is no longer neutral. The overall charge is no longer 0. Instead, the overall electrical charge is -1. It is a negatively charged particle. Now, this was achieved by the fluorine atom gaining an electron. But atoms can also lose electrons. And so, therefore, there are 2 different ways to become an ion. A cation is defined as an ion that has more protons than it has electrons. And because of this, a cation is positively charged. It has a larger number of positively charged protons than it has negatively charged electrons, so it has an overall positive charge. On the other hand, an anion has more electrons than it has protons, and therefore it is negatively charged. It has more negatively charged particles than it has positively charged particles, so overall it comes out negatively charged. An easy way to remember the distinction between cation and anion is if, like me, you like cats, then you can think that a cation is positively charged because cats are positive. And if you don't like cats, that won't help you, or maybe it will. Hopefully you can just remember it. In the example that we just talked about with the fluorine atom, we saw it gaining 1 electron, and so that means that it had 10 electrons in the orbitals and 9 protons in the nucleus. So that would mean, out of these 2 categories, cation or anion, which one is the fluorine ion? Well, it would be an anion, because it has more electrons than it has protons. It gained an electron, and therefore it is a negatively charged anion. Now we're going to tackle a few checkpoints related to terminology that we've just gone over. So what I want you to do in this checkpoint is fill in the blanks. Atoms of the same what all have the same number of what's, while their blank and blank may vary. And one more fill in the blank checkpoint. Carbon, as we saw before, may have a mass of 12, 13, or 14, and these all represent different what's of carbon. And the difference in their masses is due to different numbers of what located in the where. And lastly, we have this checkpoint, which is a little bit tricky, so take your time on this one. Ions of magnesium usually have a charge of +2. So this means that they are a cation with a charge of +2. How many electrons are found then in a magnesium ion? And you have a little bit of information down here that will help you with this. From this square, you can find the number of protons in a magnesium atom, and that should help you answer how many electrons are in a magnesium ion with a charge of +2. So now we're going to move into a new part of the lecture where we start talking about how atoms associate with each other in order to form molecules. And in order to talk about this, we need to start talking about the energy stability of atoms and electrons in particular. You already know that the electrons in an atom or an ion are organized and found in the rings outside of the nucleus called the orbitals. And you may have deduced by now that the reason why they are called orbitals is because they orbit the nucleus, kind of like our model of our solar system where the planets orbit around the outside of the sun. Now think about, in our solar system, what it is that keeps the planets in orbit. It's the gravitational pull of the sun that keeps the planets spinning in these rings around the outside of the sun. The gravity keeps the planets in place. Likewise, the reason why the electrons are held in their orbits around the outside of the nucleus is because there is an electrical attraction between the negatively charged electrons in the orbitals and the positively charged protons in the nucleus. The positives and the negatives attract each other, just like the gravity of the sun pulls on the planets, and that keeps the electrons in place in their orbitals. That being said, which electrons do you think are the ones that are the most stable? Which ones are feeling the tightest pull, the strongest pull from the positively charged nucleus? The ones that are the closest or the ones that are the farthest? It makes sense that it would be the ones that are the closest, right? The ones that are farthest away don't feel as strong of a pull from the nucleus. The ones that are closest are the ones that do. And therefore, those are the ones that are most stable. The ones in the outermost orbital are more likely to be able to leave the nucleus, break out of their orbit. But the ones in the closest orbit, those ones feel the strongest pull. If you think about magnets, if you've ever played with magnets before, you have a north and a south pole magnet. As you bring them closer together, you can physically feel the pull between those two opposite polar magnets. But if you hold them far apart, you can't feel the magnetic attraction. It's only when you bring them closer that you feel the strength of that pull. And so that means the electrons that are most stable are the ones that are closest to the nucleus because they are being pulled on the most strongly. Likewise, the ones that are farthest from the nucleus are the least stable because they have the lowest connection to the nucleus. We have a special term for the electrons that are found in the least stable outer orbital, and that is valence electrons. The electrons that are in the orbital that is farthest from the nucleus in any given atom are called the valence electrons, and these electrons are special because they are the least stable and therefore the most chemically reactive electrons in an atom. They are the most likely to be able to leave the atom and go initiate a chemical reaction with some other compound. If we look at this depiction of a potassium atom here, K is the chemical symbol for potassium, we can see that in the outermost valence, there is a single valence electron. If we look at this phosphorus atom, on the other hand, in the outermost orbital, there are 5 valence electrons. So different atoms have different numbers of valence electrons in their outermost orbital. But what unifies them is that all atoms and ions that we are concerned with are most stable when their outermost orbital contains 8 valence electrons. 8 is the magic number. 8 is the number of electrons that all atoms are in pursuit of. They all want 8 valence electrons in their outermost ring. When they don't have that, when their outermost orbital does not have 8 valence electrons, then what atoms will do is they will associate with other atoms in a way that allows them to fill their outermost orbital by either giving, taking, or sharing electrons with other molecules. And these associations are defined as molecules. Molecules are what result when atoms decide that they need to associate with other atoms in order to achieve greater stability by filling their outermost orbital with 8 valence electrons. So as we said, atoms can form into molecules by either sharing or exchanging electrons with other atoms. And of course, they do this in the pursuit of 8 valence electrons. We can see in this depiction of an atom of nitrogen that you see on the left-hand side that nitrogen has 5 valence electrons. So it is not completely satisfied. It only has 5 and it wants 8. It can get 8 if it joins together with another atom of nitrogen to form a chemical bond between the two by sharing its electrons with another atom of nitrogen. So here we have a depiction of 2 atoms of nitrogen that are engaging in a sharing of their electrons with each other. And the shared electrons are referred to as the chemical bond. So these electrons here that we are focusing on with the highlight and the arrow, that is the chemical bond between these 2 atoms in this molecule of nitrogen. The more electrons are shared or exchanged, the stronger the bond is. So in this case, we see that these 2 nitrogen atoms are each bringing 3 of their electrons to the table to share with each other. And so this is a pretty strong bond because they are sharing 3 pairs of electrons with each other. The more electrons shared or exchanged, the stronger the bond. Now there's a different name for the bonds that are formed depending upon whether a molecule is formed on the basis of sharing or exchanging. An ionic bond is formed through the exchanging of electrons between 2 atoms. So what we just saw on the last slide was sharing. An ionic bond is formed through exchanging, meaning that one atom gives up an electron and the other one receives it. This, of course, will throw off the balance of the protons that are found in the nucleus with the electrons in orbitals, and it results in the formation of 2 ions that have electrical charges, which is why these are called ionic bonds. Ionic bonds form between an atom that belongs to a non-metallic element and another atom that belongs to a metal element. And if we look at the periodic table, these metals and nonmetals are actually organized in a way that some periodic tables will show you. In this periodic table, all of the metals are highlighted in silver. And this includes things like gold, cadmium, titanium, copper, iron. All of these things are metallic elements. The nonmetals are shown in this bronze color, and this includes things like carbon, nitrogen, oxygen, sulfur, chlorine, all things that we would recognize as not metal. So ionic bonds form between something that is in the metal category of the periodic table and something that is in the non-metal category of the periodic table. Let's take a look at that example that we saw on the previous slide. So here we had an ionic bond forming between an atom of sodium, which is in fact a metal, and an atom of chlorine, which is not a metal. What we can see going on here is that from the very beginning, sodium has a single valence electron in its outermost orbital, just one. And so if you think about what its chances are of getting to 8 valence electrons, it would have to gain another 7 electrons in order to get to 8, and those chances are pretty low. However, if you look at the valence level underneath the outermost orbital, This level, the second most outer level, has 8 valence electrons already in it. So sodium actually has a better chance of getting to an outermost orbital of 8 if it simply gives up on and scraps this one electron in its outermost orbital and gives it away to some other atom. In this case, that atom is chlorine. If we look at the base state of a chlorine atom, it normally has 1, 2, 3, 4, 5, 6, 7 electrons in its outermost orbital. And that means it is very, very close to getting that desirable 8. All it needs is one more electron from somewhere in order to achieve 8. And it gets that one electron from sodium. Sodium donates its one electron to chlorine, giving chlorine a negative charge and sodium a positive charge. And as a result, chlorine now has 8, and sodium has lost its outermost orbital entirely, making the next level its true outermost orbital, which already contains 8 electrons. So in this exchange, both sodium and chlorine are satisfied. So that's an example of a bond, an ionic bond, that forms through the exchanging of electrons. And now we're going to talk about the opposite situation, where instead of exchanging electrons, the atoms participating in the chemical bond share them. This is not called an ionic bond, it is called a covalent bond. So a covalent bond is formed by sharing at least one pair of valence electrons between atoms. Covalent bonds work because the atoms engaged in them can kind of cheat and double dip. They can count both their electrons and their partner's electrons toward their outermost valence. And these types of bonds occur not between a metal and a nonmetal, but rather between two or more nonmetals. So no metals are involved here. These types of bonds occur between elements that belong to the bronze section of the periodic table, along with other ones that also belong to the bronze section. No metals are involved in covalent bonds. Let's take a look back at that example of nitrogen sharing electrons with another nitrogen that we saw a few slides ago. So we saw that nitrogen normally starts out with 5 valence electrons in its outermost orbital. This we can see on the left here. And we know that with 5 it is not satisfied, and so what it can do is get together with another nitrogen, which also has 5, and they can share 3 each of their electrons and bring 3 to the table. Now in this picture right here, we see that the atom on the left has its electrons depicted as little x's, whereas the atom on the right has its electrons depicted as little circles. If we look at the atom on the left, it is sharing 3 of the little circles that were brought to the table by this nitrogen on the right. And so we can count its valence electrons and say it has 1, 2, 3, 4, 5, 6, 7, 8. Because the electrons that it owns, as well as the ones that it is borrowing, count toward its outermost valence. On the other hand, the atom on the right of nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 as well, because it counts its little circles as well as the little x's from the nitrogen on the left. So in making this sharing arrangement, both nitrogens are satisfied and can say that they count as 8 valence electrons. So this brings us to a checkpoint. We have a number of different molecules displayed on the slide here. We have water, magnesium sulfate, and methane. And what I want you to do is look at the bonds that we have in each of these compounds and tell me whether they are ionic bonds, where the atoms involved are exchanging electrons, or if they are covalent bonds, where the atoms involved are sharing electrons with each other. Is each one ionic or covalent? So now we've talked about atoms, we've talked about how atoms form molecules, and the different types of bonds in which they can engage, either ionic or covalent as they form molecules. Now we're going to take a little bit deeper of a dive into covalent bonds, the ones in which electrons are shared, where we talk about a concept called electronegativity. Because the reality of the fact is that when atoms form covalent bonds, their electrons that each atom brings to the table are not always shared equally. In fact, some atoms, some elements, are better sharers than others. The way that shared electrons end up being distributed between atoms that are engaging in a covalent bond depends upon the strength of each atom's electronegativity. Electronegativity is a word that essentially means how badly each element in the bond wants electrons for itself. It's a measurement of how electron greedy an element is. Every element on the periodic table has a specific level of electron greediness, which can be different from other elements on the periodic table. The version of the periodic table that you're going to see on the next slide is different from a typical periodic table because instead of showing you things like the atomic number and the atomic weight, it instead shows you a single number which represents how electron greedy each element is. The higher the number, the greater level of electronegativity or electron greediness. So if we look at this periodic table, we can see that the elements with the highest level of electron greediness tend to be clustered in the upper right-hand corner of the periodic table here, whereas the atoms with the lowest level of electron greediness are clustered down here, and then there's a distribution of various numbers somewhere in the middle here. So the ones in the upper right want electrons very, very badly. They have a very high electronegativity, whereas ones over here do not. The ones over here tend to be very bad sharers because they are very electron greedy. And when they get together in a bond with another element that is not as greedy as they are, then they tend to form very unequal distributions of the shared electrons. For example, if we have a bond between an element like fluorine, which has the highest electronegativity of any element on the periodic table, clocking in at 4.0. If we have a bond between fluorine and hydrogen, which has a much lower level of electron greediness here, they each bring electrons to the table to share, but fluorine has a much greater desire or want for electrons than hydrogen does, and so they share those electrons unequally. The electrons tend to be pulled more strongly toward the more electronegative or the more greedy atom, which in this case is fluorine. This results in what are called an electron poor region of the molecule and an electron rich region of the molecule, because this greedy fluorine is drawing those electrons toward itself, leaving hydrogen with a lower quantity of electrons. For this reason, this type of bond, where electrons are shared unequally, are described as polar covalent bonds. And the reason why they're described as polar is, well, think about what the word polar means in everyday language. Polar means opposite ends, right? We can think of other words like polar bear, the poles of the earth, bipolar. It means opposite ends. So we have two opposite ends here which are different in their level of electron richness. We have one pole that is electron rich and one pole that is electron poor. And this happens when you get a very greedy atom together with a not so greedy atom. This isn't always the case, of course. Sometimes you can get atoms together in covalent sharing bonds, and they have relatively similar electronegativities. And in this case, they would share their electrons relatively equally. Here we have an example of hydrogen, again, like we saw on the last slide, in a covalent bond with boron. And as we can see, hydrogen still has a 2.1 electronegativity rating, and boron has a 2.0. So they're very similar to each other. We don't have this imbalance of an extremely electron greedy atom together with an extremely electron not greedy atom. This means that when they share their electrons that they both bring to the table in this covalent bond, the electrons will be distributed evenly, and therefore the resulting molecule won't have those extreme electron-rich versus electron-poor ends to it. These types of bonds are described as nonpolar covalent bonds because they don't have opposite ends. Everything is smooth, everything is even. The electrons are distributed equally, and everyone is happy because neither of the atoms in this bond are particularly electron greedy. Now let's take a look back at those polar bonds again. We saw that in the polar covalent bonds, there was an unequal distribution of electrons so that one end had a larger quantity of electrons and the other had a lower quantity of electrons. This means that the end of the molecule that has more electrons gathers an overall negative charge associated with it, because as you remember, electrons have a negative electrical charge. On the other hand, as the electrons are drawn away from the other side of the molecule, there are fewer electrons, and the remaining protons give that end of the molecule an overall positive charge. These negative and positive ends within the same molecule are referred to as dipoles, which literally means the two poles. Now, molecules don't exist in isolation. I told you that there are 7 to the 27th power molecules in the human body. So molecules exist in samples, large quantities, where they're always bumping into each other and coming into contact with each other. When you have large quantities of polar molecules in association with each other, then because of this existence of dipoles, the negative end of one molecule is attracted to the positive end of another molecule because of the existence of those dipoles. This phenomenon does not take place in nonpolar molecules because there's no attraction between them. The electrons are distributed evenly, meaning that the dipoles don't exist. There are no negative or positive charges that would cause a molecule of hydrogen and boron to be attracted to another molecule of hydrogen and boron. That just doesn't happen. It does happen in samples of substances that are made up of polar molecules, like these ones right here. And it happens especially with 3 particular pairs of elements when they engage in covalent bonds with each other. There are 3 pairs of elements which, when they bond and share electrons with each other, result in extremely unequal electron sharing. These are the 3 worst pairs of sharers on the periodic table. These 3 pairs are hydrogen and fluorine, as we saw, hydrogen and oxygen, and hydrogen with nitrogen. These 3 pairs, more so than the other pairs that could potentially bond on the periodic table, share electrons the most unevenly. Within molecules that contain these pairs of the 3 worst sharers, the result is that positive and negative ends, positive and negative dipoles, are created in this molecule, which are so dramatic and so strong that separate molecules exhibit a high level of attraction to each other. That attraction is so strong that it was actually given the name a hydrogen bond. If we were to point to where the hydrogen bond is in this diagram right here, it's right here. It's the dotted green line between the separate molecules. And I want to be clear because some people think that the word bond means that it's within the molecule, but it is not. The hydrogen bond is between this molecule over here and this molecule over here. Within each molecule, there is a polar covalent bond between the hydrogen and the fluorine. But the hydrogen bond is a name for this strong attraction between separate molecules. It is called a hydrogen bond because if we take a look back at the set of the 3 worst sharers, Each of them contains hydrogen as one of the unequal partners in this sharing arrangement. So therefore, the attraction between the separate molecules has been deemed a hydrogen bond. So compounds that contain at least one of those three pairs, that is H with F, H with O, or H with N, there is a high level of attraction between separate molecules within those samples. Here we have the example of the chemical compound ammonia, which has the chemical formula NH3, which is a nitrogen bonded to 3 hydrogen atoms. This, of course, is one of the pairs that results in extreme unequal electron sharing, a hydrogen bonded to a nitrogen. And within those pairs, it is the nitrogen that is the electron-greedy partner. So therefore, within these arrangements, the nitrogen pulls all of the shared electrons toward itself, which leaves the hydrogens with more protons than electrons and an overall positive charge. Now, ammonia is a cleaning compound that you may have in your own house. So when you have a jug of cleaning ammonia, it's not just one molecule in there, but rather it is hundreds of thousands of molecules that are all sloshing around together and bumping into each other. And when they do that, the negative end of one molecule, the nitrogen of one, is highly attracted to the hydrogen of a separate molecule because of these positive and negative dipoles within the molecules. Therefore, they experience hydrogen bonding between separate molecules in a sample, and it's very, very difficult to pull those separate molecules apart from each other. So in this checkpoint here, we have 3 separate chemical compounds. We have methane, tetrafluoromethane, and ethanol. And what I want you to do is tell me, out of these 3, are any of them capable of hydrogen bonding? Do any of them meet the qualifications and the requirements to be able to hydrogen bond with other molecules like itself? In other words, can methane hydrogen bond to other molecules of methane? Can tetrafluoromethane hydrogen bond to other molecules of tetrafluoromethane? And can ethanol hydrogen bond to other molecules of ethanol? So by now I think we've digressed far enough away from our central question in this lecture, which is about the chemical foundations of life, and it's time to bring it back to that question by discussing the most important hydrogen bonding molecule, which is, of course, water. A molecule of water is H2O, meaning that it is made up of 2 hydrogens that are covalently bonded to and sharing their electrons with an oxygen atom. However, they're not sharing their electrons equally because oxygen is very electron greedy and hydrogen is not. Oxygen, of course, pulls the electrons toward itself, making that end of the molecule negatively charged and leaving the hydrogens more positive. And when you get samples of water molecules together, then the water molecules are highly attracted to each other between the oxygen of one molecule and the hydrogen of another molecule. And it makes them very difficult to pull apart. Within any sample of water, there is this invisible network of attractions between separate molecules that makes them very tightly knit. And this tight-knit nature of water molecules actually gives water some important characteristics and properties that are not seen in other substances and that are essential for supporting life on Earth. In total, there are 5 special properties of water that allow this substance to be necessary and supportive of life as we know it. So in the final part of this lecture, what we're going to be doing is talking about those 5 properties and how they result from the ability of water to do this thing that we call hydrogen bonding. The first of these properties is that solid water is actually less dense than liquid water. This is not normal. The solid form of water, which is ice, is less dense and floats on top of the liquid form of water. With most substances in the universe, that is not the case, and the solid form of that substance sinks to the bottom of the liquid form. The reason why this happens is a result of hydrogen bonding. In liquid water, hydrogen bonds are constantly breaking and reforming as the water molecules move around each other, but as water solidifies, the hydrogen bonds become stabilized and they hold the water molecules at a particular distance from each other. And this causes the water molecules to become spaced out more so than when they are in liquid form. The extra space that is created by the hydrogen bonds when water is solid makes the solid water less dense than liquid water and means that it floats. Now, why would this be important and essential for life on Earth? You probably know that when bodies of water freeze, only the top layer of that body of water will freeze over. This is the principle behind ice fishing, for example. The reason why ice fishing works is because you can walk out onto the ice and drill a hole down to the liquid level of the water because the body of water has not frozen solid. Only the layer on top freezes solid. What would happen if solid water was more dense than liquid water? What would happen if the opposite was true and your ice sank to the bottom of your cup instead of floating on top? Well, what would happen is the top layer of a body of water would freeze, and then it would sink to the bottom. Then the process would repeat. The top layer would freeze and sink to the bottom. And as this happened over and over again, entire bodies of water, such as lakes or oceans, would freeze solid. And that's not what happens today, because solid water is less dense than liquid water. The fact that solid water is less dense than liquid water, and the fact that bodies of water only freeze at their top layer while the remaining water remains liquid underneath, makes it possible for life to persist through seasonal temperature changes. Underneath that layer of ice on top, you still have all of the fish, all of the aquatic plants, all of the life going on under the surface of the ice. And if that body of water froze solid, that would not be the case. So this is why the property of solid water being less dense than liquid water because of hydrogen bonding is essential for life on Earth. It allows for bodies of water such as lakes, oceans, etc. to not freeze solid during temperature changes. The next special property of water that results from its ability to hydrogen bond is that it resists changes in temperature and is able to maintain a stable temperature even when there are exterior temperature changes. A perfect example of this is if I ask the question, which would you rather do in the heat of the summer in Arizona here? Would you rather dive naked into your swimming pool, or would you rather lie naked on the hood of your car? The obvious answer is that you don't want to lie naked on the hood of your car because it's burning hot. You would rather dive into your swimming pool. And the reason why the temperature of your swimming pool is so different from the temperature of the hood of your car comes back to hydrogen bonding. We know that in hydrogen bonds, molecules are very tightly knit and difficult to pull apart from each other. What happens when the temperature of a substance increases is the molecules start to get physically excited and they start to vibrate and move around. As more and more heat is absorbed by molecules, that means that they become more agitated and they move faster. In molecules where samples are hydrogen bonded to one another, this process is resisted because the molecules are held together very tightly by their attractions to like molecules. Within a sample of water, like that in your swimming pool, even as the sun beats down on it and infuses it with heat, the molecules remain cool because they are not vibrating and getting excited like the molecules on the hood of your car, as a result of the hydrogen bonds that connect the molecules of water in the sample. Likewise, for the same reasons, we're brought to property number 3, which is that water resists changes in state. This means that it resists transitions from solid to liquid to gas. And when a sample transitions from solid to liquid to gas, what's happening on a molecular level is the molecules are spreading out. When you boil a pot of water on your stove and it goes from being a liquid to a gas, what happens to the water molecules is that they spread out from their concentrated area inside of the pot to being water vapor all throughout your kitchen. Unlike other substances, water resists this process. It resists evaporation. And that's important for life on Earth because with temperature changes all around the globe, you wouldn't want entire bodies of water to evaporate and change temperature very rapidly. The fact that water resists changes in temperature and state is very important for living organisms because we can walk outside in the middle of the summer and all of the water in our bodies doesn't evaporate, or the oceans don't evaporate and then recondense when it gets cool. This is important for the stable maintenance of bodies of water on Earth. Fourth property is that polar molecules dissolve really well in water because water itself is polar. What you can see in this animation right here is a person dumping some salt into a glass of water and then stirring it up. And you can see that after a few seconds of stirring, the salt begins to dissolve and disappear, and the water will look clear. You can't even tell that the salt is in there because it has been dissolved. On a molecular level, what makes this possible is the hydrogen bonding and polar nature of the water molecules. Here's an animation of what's happening on a molecular level inside of that glass of water. The water molecules here are represented by the little accumulations of white and red balls, and then a grain of salt is represented as that big cube made up of positive and negative green and white charges there. You can see that the water molecules are essentially attacking that cube of salt and pulling apart piece by piece on a molecular level the salt block. The reason why this happens is because water is a polar molecule. The water molecules, having these attractions, are able to then use those attractions to pull apart the pieces of the grain of salt and effectively cause it to dissolve in the sample of water. Why is this important for living organisms? Well, you may know that our bodies are mostly composed of water by mass. All of your digestion, all of your circulation, all of the chemical reactions that happen inside of your body are happening essentially inside of water. The fact that your body can dissolve polar molecules really well is essential to all of our functions because all of our chemical reactions that allow us to live are happening inside of this giant bag of water that is our body. And without the ability of water to dissolve these polar molecules, those reactions would not be able to happen. Now, last but not least, the fifth and final property of water that arises from its ability to hydrogen bond is kind of the opposite of the fourth property. And that is that nonpolar molecules do not dissolve well in water. Property number 4 was that polar molecules, ones that have unequal covalent bonds, dissolve well in water, but nonpolar ones do not. And this has to do with something called the hydrophobic effect, which you probably have recognized in your everyday life. The hydrophobic effect describes the tendency of nonpolar molecules to avoid water because they cannot dissolve in it. The word hydrophobic literally means afraid of water, and it describes molecules that will separate themselves from water, such as oil, for example, on the surface of this glass of water. If you've ever had an oil and vinegar salad dressing and you notice that after some time sitting in your fridge, it separates into 2 different levels. There's the level of the oil and the level of the water, and you have to shake it to mix them up. The reason why that happens is because of the hydrophobic effect and because Water can hydrogen bond, therefore nonpolar molecules do not dissolve well in it. It has no attraction to these molecules. Now, the reason why this is important for living organisms takes a little bit more explaining, so that's what we're going to do on the next few slides. It turns out that the hydrophobic effect is essential for the formation of the essential unit of living organisms, which is cells. All living things are made of tiny structures called cells, which we will elaborate more on in future chapters. But those cells are surrounded by a layer of membrane composed of what are called phospholipids. So this barrier that you see right here, this represents the membrane of the cell, which defines its borders. Inside of the cell is filled with water. Outside of the cell, there is water. And the material of the membrane is made up of these molecules called phospholipids. Phospholipids are a very interesting type of molecule because they have this duality about them, where one part of the molecule is polar and the other part of the molecule is nonpolar. In other words, in one part of this molecule, electrons are shared unequally. In the other part, they are shared equally. And here's what a phospholipid looks like. It kind of looks like this little jellyfish thing. It's got what's called a head here, where electrons are shared very unequally. This is the polar end of the molecule. And then over here, electrons are shared equally in the nonpolar tails, of which there are two. So the fact that this molecule has opposing ends, at one end it wants to dissolve in water, and the other end it wants nothing to do with water. This is essential for the formation of these cell membranes, because when you get a large quantity of these little phospholipids together, they will spontaneously organize themselves into a double layer called a phospholipid bilayer, which satisfies the unique chemical needs of each end of the phospholipid. We know that there is water inside of the cell and that there is water outside of the cell. We also know that the head of the phospholipid can dissolve in water, whereas the tails of the phospholipid are hydrophobic and want to avoid water. Therefore, when you get large quantities of phospholipids together in a sample, they organize themselves into a structure which allows the polar heads to be exposed to the water inside and outside of the cell, while the nonpolar tails facing each other can be protected from exposure to water by the layers of the heads. And this is what a cell membrane looks like. So therefore, these last two properties, number 4 and number 5, which is that polar dissolves in water and nonpolar does not dissolve in water, these two properties lead to the formation of cell membranes, which are the fundamental unit of life. So in this checkpoint here, what I want you to do is choose one of the special properties that we just talked about that result from hydrogen bonding in water and describe to me in detail how it is essential for living organisms. So the last sort of miscellaneous topic that we need to cover in this lecture before we are finished, and we are almost finished, we only have a few slides remaining. The last miscellaneous topic is that of acids and bases. Because acids and bases are an important part of living organisms that we will be discussing in the future. Acids and bases, you may know, are measured on what's called the pH scale. But what you may not know is that the pH scale actually measures the amount of hydrogen ions present in a solution. That's what the H in pH stands for, is the hydrogen ions. Hydrogen ions are the same thing as protons. So recall that an ion is an atom that has either gained or lost electrons. But hydrogen, being the smallest element on the periodic table, is only composed of a single proton in its nucleus and a single electron in its orbital. When it loses that electron and it becomes an ion, all that remains is a single free proton. And therefore, a hydrogen ion is the same thing as a proton. The lower the concentration of free protons in a solution, the higher the pH, and vice versa. The higher the concentration of protons in a solution, the lower the pH. This is the basis for the measurement of acids and bases and their strength. Here's a representation of the pH scale and where some common substances fall on it. Neutral is considered the number 7 because the pH scale only runs from 1 up to 14. 1 is the strongest acidic substance, and 14 is the strongest basic substance. 7, lying directly in the middle, is pure water, which is neither acidic nor basic. As you go farther left on this scale to a lower pH number, substances become more acidic and have a higher concentration of hydrogen ions or protons in them. On the other hand, as you go right away from 7 and go into the more basic territory with a higher pH, there is a lower concentration of hydrogen ions in the substance. So we have one final checkpoint to round us out on this topic of acids and bases. Here I have two common substances that you're probably familiar with. We have bleach on the left, which sits at a pH of about 12, and Dr. Pepper on the right, which sits at a pH of 2.5. Tell me, out of these two, which has a higher concentration of hydrogen ions in it? When you've completed this checkpoint, then you are finished with the Chapter 2 lecture, and I will see you in the next lecture.